Hi, this is Xiaochu at Lehigh University. Today we're going to talk about the homework 5. Let's take a look at the first problem. The valve in an oil pipeline must be closed rapidly when a leak is detected, but not so fast as to produce a large pressure rise. The length of the oil pipe is 125 meters. The diameter of the pipe is 0.5 meter. The thickness of the pipe is 25 centimeter. And the elasticity of the pipe, because the pipe is made by the steel, based on the table 4.1, we can find the elasticity of the pipe is equals to 1.9 times 10 to the power of 10. And the elasticity of the oil is given, which is 1.5 times 10 to the power of 9. The specific gravity is equals to 0.85. The density of water is 998 kilogram per square meter. The flow rate in the pipe is 1.65 cubic meter per second. In this problem, we want to determine the minimum valve closure time that would prevent a large pressure rise, which is to prevent the rapid closure. Before solving this problem, let's analyze this problem first. This problem asks us to calculate the minimum time to prevent rapid closure. Based on the equation 1 here, we know the definition of the rapid closure is the close time less than 2 times length over celerity. Therefore, we know that the minimum time to prevent rapid closure is equals to 2 times length over celerity. And in equation 1, we already know the length, but we do not know the celerity. So to solve the minimum time, we need to know the celerity first. And the celerity can be calculated by using the equation 2. In equation 2, the celerity is related to the composite elasticity of the system and the density of the oil. Let's take a look at the density of the oil first. We can calculate based on the specific gravity times the density of the water. And composite elasticity of the system we can calculate based on the equation 3. In equation 3, the elasticity of the oil and elasticity of the pipe, the thickness of the pipe, the diameter are all given. The only unknown is the constant K. And constant K, we can use the equation 4 because this pipe is anchored by expansion joints based on the equation on 126. The K equals to 1 minus 0.5 times sigma. Sigma is a Poisson parameter. For the common materials, the sigma typically equals to 0.25. After we analyze this problem, in this flowchart, we can see that if we calculate each parameter in a reverse order, then finally we can get a minimum time to prevent the rapid closure. So let's calculate the density of the oil first. Based on equation 5, it equals to the specific gravity times the density of the water. It equals to 0.85 times 998 kilo per square meter. The density of the oil, it equals to 848.3 kilogram per square meter. Then, based on the epsilon, we can calculate K. And then to calculate bring it to the equation 3 to calculate the composite elasticity. K equals to 1 minus 0.5 times epsilon. It equals to 1 minus 0.5 times 0.25. Then the K equals to 0.875. After we bring it to equation 3, which is E sub C equals to 1 over E sub B plus D times K over E sub P times E. We can get it equals to 1 over E sub B is 1.5 times 10 to the power of 9 plus the diameter is 0.5 meter times K is 0.875 over E sub P is 1.9 times 10 to the power of 11 times the thickness is 0.025. Then we can get the composite elasticity of the system. It equals to 1.32 times 10 to the power of 9 Newton per square meter. Okay, so currently we have these two values. Then we can calculate the celerity based on the equation 2. The celerity, it equals to the square root of the E sub C over the density of the oil. It equals to 1.32 times 10 to the power of 9 over the density of the oil is 48.3. Then we can get the celerity. It equals to 1,246 meter per second. And then we can bring this value back to equation 1 because currently we have the length and the celerity. Then the minimum time equals to 2 times length over celerity. The length is 1,250 meter. The celerity is 1,246 meter per second. Then we can get the minimum time. It equals to 2 seconds. So which means that if the closure time less than the minimum time, which is 2 seconds, it is a rapid closure. So the minimum time to prevent the rapid closure is 2 seconds. Let's take a look at the problem 2. Here is a water pipeline connecting two reservoirs. The length of the pipe is 1,200 meter. The diameter is 0.5 meter. The thickness of the pipe is 0.02 meter. Because the pipeline is made by the ductile iron, based on the table 4.1, we can find the elasticity of the pipe. It equals to 1.610 to the power of 11. And based on the information given on page 9, we can find the elasticity of the water. It equals to 2.2 times 10 to the power of 9. The water density is 998 kilo per square meter. The flow rate in the pipe is 1.35 cubic meter per second. And the problem asks us to determine the maximum water hammer pressure if the valve is closed in 1.5 seconds. Before solving this problem, let's analyze the unknown and given information first. In this problem, we want to know the maximum water hammer pressure, which is delta P. To select the equation to calculate delta P, we need to know if the rapid closure situation happens. To do that, we need to calculate the value of the minimum pressure and then compare it with the time for close the valve. And based on equation 1, to calculate the minimum pressure, we need to know the length and the celerity. In this problem, the length is already given. We need to consider the celerity only. And we can calculate the celerity based on the equation 2. In equation 2, we know the density of water, and then we need to calculate the elasticity of the composite elasticity of the system, which is given by equation 3. In equation 3, the elasticity of the water, the pipe, the thickness of the pipe, and the diameter are all given. We only need to calculate the constant K. And because the problem told us it is free to move longitudinally, and based on that information on the page 126, we can calculate the constant K, it equals to 1. Okay, based on the flowchart we already have, let's calculate each parameter in a reverse order to calculate the delta P. So first, we want to calculate the composite elasticity of the system. 1 over E sub C, it equals to 1 over E sub B plus the diameter times the constant over E sub P times the thickness E. If we bring the value into this equation, we can get the E sub B, it's 2.2 times 10 to the power of 9 plus the diameter is 0.5 times the K is 1 over E sub P is 1.6 times 10 to the power of 11 times E is 0.02 meter. Then we can get E sub C, it equals to 1.64 times 10 to the power of 9 Newton per square meter. Then the next step is to bring the E sub C into equation 2 to calculate the celerity. The equation 2 is celerity equals to square root to E sub C over the density of water. It equals to 1.64 times 10 to the power of 9 over the density of water is 998 kilogram per square meter per cubic meter, and the celerity C, it equals to 1,280 meter per second. after that, we can use the length and celerity to calculate the minimum time to prevent the rapid closure. So the minimum time equals to 2 times L over C. It equals to 2 times L is 1,200 meter over the celerity is 1,280 meter per second. Then we can get the T minimum. It equals to 1.88 seconds. And we need to compare the minimum time with the time that given in the problem. Because the time to close the valve, it equals to 1.5 seconds, which is smaller than the minimum time to prevent the rapid closure. So there is a rapid closure happened. And because the rapid closure happened, then we can select the equation 5 on the textbook to calculate the maximum water hammer pressure. The delta P, it equals to the water density times the celerity times the velocity. Then we can bring the value back into this equation. Then it equals to 998 times celerity is 1,280 times the flow rate is 1.35 over the area. Area is pi times d squared. D is 0.5. Then we can get the delta P. It equals to 8.79 10 times 10 to the power of 6 Newton per square meter. Then the maximum water hammer pressure is 8.69 times 10 to the power of 6 Newton per square meter. So let's take a look at the problem 3. In this problem, we know the diameter of the pipe is 8 inch and the pipe is made by the ductile iron. So based on that information, we can find the elasticity of the pipe on page 4.1, which is equal to 2.3 times 10 to the power of 7 psi. And the pipe is designed to withstand a water hammer pressure of 250 psi. So the delta P, it equals to 250. The operational head is assumed to be negligible. The pipeline is anchored at both ends. So based on the equation given on page 126, we can calculate the constant k. It equals to 0.938. And we also know the design flow rate in this pipe, it equals to 1.45 cubic feet per second. And we assume that it is in room temperature. Therefore, the density, water density, it equals to 1.94 slug per cubic feet. So in this problem, it asks us to determine the required pipe thickness, which is E. Let's analyze the given information and the unknown before solving this problem. In this problem, we want to know the thickness. If we go through the equation listed here, we can find that the thickness can only found in equation 3. Let's take a look at equation 3. The elasticity of the water, elasticity of the pipe, the diameter and the constant K are all given. Therefore, by using this equation, we need to use this equation to calculate the thickness E, we need to get the value of the composite elasticity of the system first. Therefore, we need the equation 2 to calculate the composite of elasticity of the system. In this equation, the water density is already given, and we need to calculate the celerity. Because the problem provides us the information about the delta P. So in equation 5, we know the delta P, the density of the water, and we want to know the value of the celerity. Then we need to calculate the velocity of the water. Because we already know the velocity of the water equals to the flow rate over the cross-sectional area. The flow rate and the diameter are all given. Therefore, we can start to solving this problem. So we need to calculate each parameter in reverse order. The first step is to calculate the velocity. The flow rate is 1.45 cubic feet per second. The area is 1/4 times pi times d squared. D is 8 inch. So we need to divide 12 because the unit transformation. And we can get the velocity. It equals to 4.15 feet per second. So currently we have the velocity, and then we bring it back to equation 5 to calculate the celerity. delta P, it equals to the density times the celerity times the velocity. The delta P, it equals to 250 psi. And it equals to 36,000 pound per square feet. The density, it equals to 1.94 slug per cubic feet. We just calculate the velocity, it equals to 4.15 feet per second. Then if we bring these three values back into the equation, we can get the celerity. It equals to 4,470 feet per second. Then based on equation 2, we can calculate the composite elasticity is here. The celerity equals to square root to the composite elasticity of the system over the water density. Because the celerity, it equals to 4,470 feet per second. The water density, it equals to 1.94 slug per cubic feet per second. Cubic feet, sorry. If we bring the value back into this equation, we can get the composite elasticity of the system. It equals to 2.69 times 10 to the power of 5 pound per square inch. And then we have the composite elasticity. We can calculate the thickness of the pipe based on the equation 3. Diameter times constant K over the elasticity of the pipe times the thickness. The composite elasticity of the system, it equals to 2 times 69 times 10 to the power of 5 pound per square inch. The elasticity of the water, it equals to 3.2 times 10 to the power of 5 pound per square inch. And the elasticity of the pipe, it equals to 2.3 times 10 to the power of 7 psi pound per square inch. The diameter of the pipe it equals to 8 inch. And the constant K we calculate here, it equals to 0.938. If we bring the value back to this equation, we can get the thickness. It equals to 0.6626 inch, which is close to 0.7 inch. Therefore, the required pipe thickness to account for any operational pressure should equals to 0.7 inch. Let's look at the problem 4. A surge tank is being designed to retard the water hammer in a pipe. The length of the pipe it equals to 3,450 feet. The diameter of the pipe is 6.5 feet. And the water elasticity it equals to 3.2 times 10 to the power of 5 pounds per square inch. We can find this information on page 9. And because the pipe is made by the smooth concrete, then we can find the elasticity of the pipe on page 128. It equals to 2.5 times 10 to the power of 7 pounds per square inch. And we can also find the roughness of the pipe. It equals to 0.0006 feet on page 66. The flow rate in the pipe it equals to 460 feet. And the viscosity of the water it equals to 1.08 times 10 to the power of minus 5. We can find it on page 6. In this problem, it asks us to determine the diameter of the surge tank if the water in the tank is allowed to rise to an elevation 16.5 feet above the feeding reservoir after the flow is suddenly stopped. Therefore, the Y max it equals to 16.5 feet. We want to calculate the diameter of the surge tank, which is represented by the d sub s. Let's analyze the unknown and the given information before we solving the problem. In this problem, it asks us to calculate the d sub s, which is the diameter of the surge tank. If we can get the area of the surge tank, we can calculate the diameter because the area it equals to 1/4 times pi times d square. Then we can find the a sub s in equation 1. In equation 1, the length, the area of the pipe are given. We do not know the k sub f and the damping factor beta. So, to solving the area of the surge tank, we need to know the value of the k sub f and the damping factor. Let's look at the k sub f first. If we write down the Darcy-Weisbach equation, we can find the friction loss. It equals to the friction factor times L over D times the velocity head. If we bring all the constant value together and set it equal to K sub F, then we can rewrite the Darcy-Weisbach equation. It equals to K sub F times velocity squared. If we want to, based on this equation 3, if we want to get the value of K sub F, we need to know the value of the friction loss. And the friction loss is based on the friction factor, which is related to the relative roughness, the Reynolds number, and also the velocity. Now let's take a look at the damping factor beta in equation 2. In equation 2, we already know the Y max. It equals to 16.5 feet. We do not know the beta and the head loss, because in this problem, the minor losses can be negligible. Then the head loss should equals to the friction loss. Therefore, to solving the damping factor beta, we also need to calculate the value of the head loss first. Now let's calculate each parameters in the reverse order. Now let's calculate the friction loss. The head loss, it equals to the friction loss because the minor losses are negligible. It equals to the Darcy-Weisbach equation. We can calculate the velocity equals to Q over A. The Q is 460 feet. It should be cubic feet per second. The area, because we already know the diameter of the pipe, we can calculate its area. It equals to 4 times 460 over pi times 6.5 square. It equals to 13.9 feet per second. And then we need to determine the friction factor, which is based on the relative roughness. The roughness, it equals to 0.006. And the diameter, it equals to 6.5. then we can get the relative roughness. It equals to 0.00092. And the Reynolds number, it equals to the velocity times diameter over the kinematic viscosity. It equals to the velocity is 13.9 feet per second. The diameter is 6.5 feet. And the kinematic viscosity, it equals to 1.808 times 10 to the power of minus 5. And it equals to 8.37 times 10 to the power of 6. And based on these two information, we can find the friction factor on Moody diagram. It equals to 0.012. Therefore, we can bring all the value back to this equation. Then we can get the head loss. It equals to 0.012 times 3,450 feet over 6.5 feet times the velocity is 13.9 square over 2 times 32.2. Then we can get the head loss. It equals to 19.1 feet. So currently we have the value of the head loss. So the next step, we need to calculate the K sub F. So based on this equation, this K sub F, it equals to 5 times L over D times 1 over 2G. After we bring the value back into this equation, we can get K sub F, it equals to 0.0989 second square per foot. Then the next step is to calculate the damping factor beta based on the equation 2. The Y max plus the head loss over beta, it equals to ln beta over beta minus Y max. And the Y max, it equals to 16.5 feet. The head loss is 19.1 feet. It equals to 1 beta minus over beta minus 16.5. Then we can calculate the value of the beta. It equals to 19.9 feet. So right now we already have the case of f and the beta. Then we can bring this two value back into the equation 1 to calculate the area of the surge tank. Beta equals to the length times the area of the pipeline over 2G times K sub F times the area of the surge tank. The beta, it equals to 19.9. The length is 3,450 feet times area. It equals to 1/4 times pi times d squared. D is 6.5 feet. Two times 32.2 times K sub F, it equals to 0.0989 times then we can get the value of K sub S. It equals to 904 square feet. And because the area of the surge tank, it equals to 1/4 times pi times the diameter of the surge tank square. It equals to 904 equals to 1/4 times pi times d sub s square. Then we can get the value of d sub s. It equals to 33.9 feet. Therefore, if the water in the tank is allowed to rise to 16.5 feet, the diameter of the surge tank should equals to 33.9 feet. Now let's take a look at problem 5. a pump is needed to quickly drain the small lake behind the dam. We already know the total energy of the pump is equals to 2.43 meter, and the power requirement for the motor is 1000 watts, and the pump motor combination has a low efficiency, which is 0.5. And the specific weight of water it equals to 9,790 Newton per cubic meter. We can find this value on the textbook. In this problem, it asks us to estimate the gel down in the first 2-hour period if the lake has a surface area of 5,000 meters. It should be noted, in this problem, it assumes that the energy head the pump must overcome doesn't change much as the lake is lowered in the first 2 hours. So in this problem, it asks us to calculate the gel down, which is the height of the decreasing water. We can calculate by using the volume divided by the surface area. In other words, in this problem, we want to calculate the volume of the decreasing water. Based on the equation 3, we can see that the volume of the water equals to the flow rate times the time. We already know the time it equals to 2 hours, which is 7,200 seconds. And the flow rate is the unknown. We need to figure it out. To calculate the flow rate, we should use the equation 2. In equation 2, we know the specific weight of water and the total energy of the pump. It equals to 2.43 meter. And we need to calculate the power of the output power. And because in this problem, the total efficiency and the power requirement for the motor are all given. Therefore, we can calculate the output power by applying the equation 1. We already know the efficiency and the power requirement for the motor. Let's calculate the output power first. It equals to the efficiency times the power requirement for the motor. 0.5 times 1000 watts. The output power it equals to 500 watts. And next step is to calculate the flow rate based on equation 2. The output power equals to specific weight of water times the flow rate times the total head of the pump. It equals to 9,790 times the flow rate equals to, the flow rate is the unknown, and the total energy, it equals to 2.43. The output power is 500 watts. Its unit can also represented by the Newton times meter per second. Then we can get the value of the flow rate. It equals to 0.021 cubic meter per second. After we got the flow rate, we bring it to the equation 3 to calculate the volume. It equals to flow rate times T equals to 0.021 times 7,200 seconds. The velocity, the volume, it equals to 151.2 cubic meter. And because the joule down, it equals to the volume over area. It equals to 151.2 over the area is 5,000 cubic meter. Then we can get the joule down. It equals to 0.0302 meter. Therefore, the joule down in the first 2-hour period, it equals to 0.0302 meter. Now let's take a look at the last problem. Here is a pump installed in a pipeline that moves water from reservoir A to B. The flow rate equals to 2.05 cubic meter per second. The length of the pipe equals to 100 meter, and the diameter is 0.8 meter. And because the pipe is made of rough concrete based on the information given on the textbook, we can find the roughness, it equals to 0.6 millimeter. And based on the diameter and the roughness, we can calculate the relative roughness equals to 0.00075. And it also told us the water surface of reservoir B is 20 meters higher than the water surface of reservoir A. And because we assume the velocity and the relative pressure at water surface equals to 0, in other words, it told us the total energy of the surface point in reservoir B minus the total energy of the surface point in reservoir A, it equals to 20 meter. And the problem also told us the pump efficiency is 80% and the motor efficiency, it equals to 74%. This problem asks us to calculate the power requirement for a motor, which is P sub m. This problem asks us to calculate the power requirement for a motor. We can find this parameter in equation 1. In equation 1, the output power equals to the power requirement for a motor times the total efficiency. Because we already know the efficiency in pump and motor, then if we time these two values together, then we can get the total efficiency. So we need to calculate the output power, then to calculate the PM. If we want to calculate the output power, let's take a look at the equation 2. It equals to the specific weight of water times flow rate times the total energy of the pump. In equation 2, we already know the specific weight of water and the flow rate is given here. So we need to calculate the total energy of the pump. Because in this problem, the pump is used to transfer the water from reservoir A to B, then we can write down the energy equation. The energy at point A plus the energy contributed by the pump should equals to the total energy at point B plus the head loss from point A to B. Because we already know the total energy at point B minus total energy at point A equals to 20 meters. Therefore, we should calculate the head loss from point A to B. Which is related to the velocity. So our first step is to calculate the velocity of the water in the pipe. It equals to the flow rate over the cross-section area. It equals to 2.05 over 1/4 times pi times d squared. D it equals to 0.8. Then we can get the velocity equals to 4.08 meter per second. Currently, we have the value of the velocity, so the next step is to calculate the head loss. The head loss, it equals to the friction loss from point A to B plus the minor losses. Because this problem, it doesn't tell us that the minor losses can be negligible. Therefore, we assume that there is a squared edged entrance. So the coefficient for the entrance, it equals to 0.5. And we should also consider the loss caused by the discharge from the pipe to the reservoir B. And from the page 79, we can find the coefficient for the discharge. It equals to 1. So the minor losses come from the entrance loss plus the discharge loss. It equals to friction factor times L over D plus the coefficient of the entrance loss plus the coefficient for discharge loss, then times the velocity head. Because we do not know the friction factor here, so the next step is to calculate friction factor based on the relative roughness and the Reynolds number. The relative roughness is equals to 0.00075, and the Reynolds number it equals to the velocity times diameter over kinematic viscosity. It equals to, the velocity is 4.08. Diameter is 0.8. The kinematic viscosity is 10 to the power of -6. Then we can get the Reynolds number equals to 3.26 times 10 to the power of 6. After that, we can read the friction factor multi-diagram. It equals to 0.0185. And we can bring all the values back into the equation. The head loss, it equals to 0.08185 times the length is 100 meter. And the diameter is 0.8. Plus the coefficient for the entrance, the squared edged entrance is 0.5. And the coefficient for discharge is 1. And then we need to times the velocity head is 4.08 square over 2 times 9.81. After we calculate this equation, we can get the value of the head loss. It equals to 3.23 meter. We have the head loss, then we can bring this value back to equation 3. In equation 3, the total energy in reservoir A plus the energy provided by the pump equals to the total energy at point B plus the head loss from point A to B. Because we know the HB minus HA equals to 20 meter. The head loss from point A to B equals to 3.23 meter. Then we can get the energy contributed from the pump. It equals to 23.23 meter. So the next step is to use the equation 2 to calculate the output power. Output power, it equals to the specific weight of water times the flow rate times the energy of the pump. Specific weight of water, it equals to, sorry, I added here. It's 9,790 Newton per cubic meter. The flow rate, it equals to 2.05. The energy of the power, it equals to 23.23 meter. If we bring this value back into this equation, we can get the output power, it equals to 466 kilowatts. Then the last step is to bring the output power into equation 1 to calculate the power, the requirement power for the motor. The output power, it equals to the requirement power for motor times the total efficiency. And the total efficiency can be represented by the pump efficiency times the motor efficiency. We already know the output power equals to 466 kilowatts. The pump efficiency equals to 0.8, and the motor efficiency equals to 0.74. If we bring these three values back into this equation, we can get the required power for the motor. It equals to 787 kilowatts. So the power requirement for a motor that is needed to drive the pump installed in a pipeline that moves 2.05 cubic meter per second from reservoir A to B is 787 kilowatts.